In this video, we're going to explore how to compute limits from formulas, and especially in some very common cases that arise in mathematics. For example, if we look at this function here, g of x, which is x squared minus 4 over x plus 2, we can see pretty quickly, if we're looking at continuity properties, that the numerator is fine. It'll be continuous everywhere, it's defined everywhere. However, we're going to have a little bit of a snag because of the denominator. And just as a pop quiz, what values are going to be problematic for the function g of x, points where the function is going to be discontinuous? Let's confirm that. Where we're worried about is x plus 2 equals 0, because if that's the case, we're dividing by 0, and that's the same as x equals negative 2. At that point, g of negative 2 is not defined, because we're dividing by 0. Now we can get a little more subtle and ask, well, what happens as we get close to that boundary point at x equals negative 2? In other words, as we get close to the discontinuity, is there a value that we're approaching, or are we having a vertical asymptote? Well, the way we express this is as a limit as x approaches negative 2 of g of x. We'll put in our formula here, x squared minus 4 over x plus 2. And we can try sort of a naive sub in here, but we already know what that's going to give us. It's going to give us 0 in the denominator, because we're going to have negative 2, let's do this carefully, negative 2 plus 2. However, in the numerator, we're going to have negative 2 squared minus 4, and that's 0 over 0, but again, that's going to be undefined. So we have to be a little more careful about this, and the way we can get more careful is by simplifying. We're still going to ask the same limit question, what happens as x approaches negative 2, but in the numerator, notice we can factor, because we have a difference of squares, into x minus 2 times x plus 2. And then we can cancel things. We can cancel these two expressions here and ask what's the limit as x approaches negative 2 of just x minus 2. And what does that look like? Well, here we can do the subbing in again, because this function is continuous. And if a function is continuous, the limit and the value are the same. We're going to end up with negative 2 minus another 2, and that's going to equal negative 4 overall. Now you should have some concern about why we can cancel these expressions here if we're worried about dividing by 0. Remember that when we're taking the limit as x approaches negative 2, we're explicitly saying that we're never going to look at x equals negative 2. We're never going to be looking exactly at the point. We're only going to be looking at all the values up to and around that point, but not exactly there. And so we're not dividing by 0 when we cancel these two terms out. We're picking values that are not 0. Just as an aside, it makes some sense to think about what this graph might look like. If we look at how we canceled things here, the graph is basically the graph of x minus 2, except with this missing piece. And if we have that at x equals negative 2, we're actually going to be down at negative 4. That was where the limit approached. This graph would go up like this. This would be the graph of g of x. It looks like the graph of y equals x minus 2, except for that one hole, that one missing point, that gets deleted because of the divide by 0. Looking at a more exotic function that involves an exponential this time, instead of just polynomials, we can see the same kind of behavior. The numerator always exists, exponentials are defined everywhere, and zeros in the numerator are fine. Where we'd have a problem here is at x equals 3, we again have a divide by 0. So what does that do for us? Well, let's take the limit again. As x approaches 3, of 7 minus e to the x over x minus 3, and we'll sub in and see what we get. We'll have 7 minus e to the 3 all over 3 minus 3. And this, if we take a look at the numerator, is around negative 13.08, divided by values that are approaching 0. And this, it's important to note, is a little different from the last case. In the last case, we ended up with a 0 over 0. We're going to spend a little more time on this later. But this is what's called, this 0 over 0 is what's called an indeterminate form. And an indeterminate form just means there's not enough information. If we're asking the limit, not does the value exist, that's clear cut. We can't plug in -2. But if we're asking what happens in the limit, and we seem to get a race of 2 zeros, one on the top and the bottom, all that means is that we have to do more work. Indeterminate forms mean go back to the start and do more work. And that's what we did here. We redeveloped the expression, we simplified it by canceling out the x plus 2's, and then we still took the limit, but of a different form of that same equation. In the case that we're looking at now, here, there's no problem at all, there's no ambiguity at all, because what we have is a number around 13 being divided by 0, and that is definitely getting larger or does not exist. So we can approach this two different ways. We could say it goes off towards infinity, or if you want to just keep it simple, DNE for does not exist. Either one of those is a perfectly valid answer for what the limit is as x approaches 3. What would that look like? We'd have to do some more sign analysis to make sure we're going the right way, but essentially the graph is either going down towards negative infinity or it's shooting up towards positive infinity at that point, x equals 3. That would be our graph with some kind of vertical asymptote. That's the kind of behavior you get when we have a nice finite number divided by 0 in the limit.